Hello, everyone. Welcome to the Analog Electronic Technology course. In analog circuits, the bipolar junction transistor is a nonlinear component, so it cannot be analyzed using the linear circuit methods learned in basic circuit courses. The graphical method and the small signal equivalent circuit method are two analysis techniques that address the nonlinear characteristics of bipolar junction transistor. Let's first introduce the graphical analysis method. The graphical analysis method helps establish key concepts such as the coexistence of AC and DC, and aids in understanding the importance of properly setting the quiescent operating point for amplifier circuits. However, it is not suitable for calculating precise performance parameters. Graphical analysis of bipolar junction transistor amplifier circuits includes two parts: static analysis and dynamic analysis. Static analysis refers to the circuit's operating state when no AC input signal is present, i.e., UI equals 0, and the circuit is powered only by DC sources. To indicate this operating state, a DC load line is drawn on the output characteristic curve. The intersection point of the two lines is marked as the Q point, also known as the quiescent operating point. The position of the Q point directly affects the output state of the amplifier circuit. Dynamic analysis refers to the circuit's operating state when an AC input signal is applied, i.e., UI is not equal to 0. Dynamic variations are usually based on the static operating point. The relationship can be visualized as a dynamic signal carried on top of the static working condition, representing the coexistence of AC and DC. Below are the steps for static graphical analysis of a bipolar junction transistor amplifier circuit. 1. Directly calculate IBQ or determine it on the input characteristic curve. 2. Draw the output characteristic curves of the bipolar junction transistor. 3. Draw the DC load line. 4. Determine the Q point. Here, we take a basic common emitter amplifier as an example. According to the above steps, write the input and output loop equations in the DC circuit. The output loop equation is called the DC load line equation. On the input characteristic curve, use the two-point method to draw the straight line where VBE equals VBB minus IB times RB. The intersection of the two lines is the Q point. An auxiliary line can be drawn to determine IBQ. On the output characteristic curve, apply the DC load line equation VCE equals to VCC minus IC times RC. Similarly, use the two-point method to draw the load line. The intersection with the previously determined IBQ curve is also the Q point. Draw auxiliary lines to obtain VCEQ and ICQ. From now on, we will mostly use the output characteristic curves to display the quiescent operating point. The DC load line intersects the horizontal axis at VCC 0 and the vertical axis at 0 VCC over RC, and its slope is -1 over RC. This completes the entire static graphical analysis process. Through graphical analysis, the DC operating state of the bipolar junction transistor can be visually determined, such as whether it is in the active region. The position of the quiescent operating point directly affects the dynamic output of the amplifier circuit. Next, let's proceed with dynamic analysis of the amplifier circuit. Based on the waveform of Vs, draw the waveform of VB on the bipolar junction transistor's input characteristic curve, with the Q point as the center line. According to the variation range of VBE, determine the threshold range of the dynamic operating points Q' and Q double prime, and sequentially determine the waveforms of IB, IC, and VC. Overall, IB, IC, and VB are in phase, while VC is out of phase with them, reflecting the inverting voltage amplification effect. When the input signal is small and the quiescent operating point is near the midpoint of the load line, the bipolar junction transistor can operate linearly throughout, with ample variation range, resulting in a true amplified output, without distortion. The above analysis is based on the proper setting of the Q point, producing a fully normal output waveform from the amplifier circuit. But what happens will occur in the output waveform if the Q point is set too high or too low? Let's demonstrate the waveform output using circuit simulation. From the simulation results, when the Q point is set too low, such as at point Q2, the upper half of the output waveform is clipped. Conversely, if it is set too high, at point Q1, the lower half of the waveform is clipped. Why does this happen? Based on theory, when the Q point is too low, i.e., IBQ and ICQ are too small, during the negative peak of the AC signal VI, the operating point moves into the cutoff region along the load line, resulting in cutoff distortion. How do we eliminate this distortion? In the circuit, by reducing the RB resistance, we can increase IBQ and ICQ, thereby raising the Q point. We verify this through circuit simulation. As the RB resistance is gradually reduced from 500 kiloohms to 100 kiloohms, the distortion gradually disappears. Likewise, when the Q point is too high, i.e., IBQ and ICQ are too large, during the positive peak of the AC signal VI, the operating point moves into the saturation region along the load line, resulting in saturation distortion. To eliminate saturation distortion, increase the RB resistance to reduce IBQ and ICQ, thereby lowering the Q point. Again, using circuit simulation, as RB resistance is gradually increased from 500 kiloohms, we can observe the gradual disappearance of the distortion. If the input signal amplitude is too large, even with the properly set Q point, both saturation and cutoff distortion may occur. The solution is to appropriately reduce the amplitude of the input signal. Thus, to achieve distortion-free amplification, the Q point must be appropriately set, ensuring that the output signal can vary linearly within the dynamic range. In addition, the graphical analysis method can be used to determine the maximum undistorted output amplitude of the amplifier circuit. This requires the use of the AC load line. In the AC path, the load resistor RL is in parallel with the collector resistor RC. Therefore, through the Q point, draw a line with a slope of -1 over RL prime. Think about this. Why does the AC load line also pass through the quiescent operating point? Because the circuit contains both AC and DC components. When the AC sinusoidal signal VI equals 0, only the DC component exists in the circuit. Hence, the AC load line also passes through the quiescent operating point. The intersection of the AC load line with the IB equals 0 output characteristic curve is the cutoff threshold, and the intersection with the saturation boundary line is the saturation threshold. Using the Q point as the center, determine the voltage differences between the Q point and these two threshold points on the horizontal axis. The smaller of the two is taken as the maximum undistorted dynamic output amplitude. Alright, that concludes our explanation of the graphical analysis of bipolar junction transistor amplifier circuits. Thank you all for watching.